Well, I hope you enjoyed the discussion on the del operator, the first new kinds of first derivatives of functions of more than one variable, and its extension to second order derivatives. Well, you'll be surprised to know that even within this short sort of 2-hour video module, we've come so far that we can actually predict what is perhaps the most important discovery mankind has ever made, which is light. So let there be light, and I'll show you in this module how all the mathematical apparatus that we have developed and studied so far is sufficient for us to actually understand that light is an electromagnetic wave, and we can actually figure out the speed of light in vacuum. So let's see how Maxwell, the pioneer who developed the mathematical machinery for us, which we can write in much more condensed form using the del operator, how Maxwell's equations enables us, and we don't need any more mathematics than what we have already covered so far. And that's the beauty of it. So let me just write down the 4 Maxwell's equations for you, and let's derive the electromagnetic wave and predict the speed of light. So the first of Maxwell's equations, perhaps I should write here, Maxwell's equations. And these are a set of 4 partial differential equations. We haven't yet talked much about partial differential equations, but in our future modules, we do plan to do that and explore partial differential equations in more detail. So, but Maxwell's equations are a bunch of 4 partial differential equations of the form del dot E, which you now recognize as the divergence of a vector field. And in this case, E represents the vector field, the electric vector field, which is the electric field. The electric field in general would be a function of x, y, z space and time. So I'm just to emphasize this, I'm going to write x, y, z, t. So the divergence of the electric field is equal to the charge density divided by epsilon naught. So rho here is charge density, which is the charge in some region of space divided by the volume of that space. And epsilon naught is called the permittivity of, in this case, vacuum, but you could have the permittivity of any material as well. And that's just how a particular material responds to an externally applied electric field. So it's a constant. We'll just take it as a constant. So that's the first Maxwell's equation. And as you can see here, the mathematical apparatus that we need to write this down is the divergence of the electric field. The second of Maxwell's equation is, again, the divergence of the magnetic field, which we denote by the symbol V. And again, this could be a function of x, y, z, and t. And it turns out that the divergence of the magnetic field is always 0. That's just the way nature is. So that's the second Maxwell's equation. The third Maxwell's equation is about the curl of the electric field. And it turns out that the curl of the electric field, I'm going to drop writing x, y, z, t all the time for now. But the curl of the electric field is the change, the time derivative, the partial derivative of the magnetic field with respect to time. And this equation couples electric and magnetic fields pretty directly. So how the change in magnetic field can give us an electric field. And the fourth equation is the inverse version of this, which is how the curl of the magnetic field is related to changes in electric field. And here you have an additional term, a new term, mu naught J plus mu naught epsilon naught, the change, the partial derivative of E with respect to T. Now, epsilon naught is the permittivity of a material, which is how a material responds to externally applied electric field. In the same way, mu naught or mu is the permeability, which is how a material responds to magnetic fields, external magnetic fields. So we don't have to go too much into the specific physical interpretation of these, but for now, these are just constants for us. J here is the electric current density. So just like rho was a charge density, charge per unit volume, J is called the current density, and that's current per unit area, the current flowing in a region per unit area. Now, these 4 equations constitute what are called Maxwell's equation. These are partial differential equations because, as you can see from these expressions, for instance, if I look at this expression, it's the divergence of the magnetic field. It says that the divergence of magnetic field is 0. And if you were to write this down explicitly, if you were to just write down del dot B in expanded notation, we'll find that it's of the form dou Bx, dou x, plus dou By, dou y, right? So del operator is dou xi plus dou yj plus dou zk. Then you dot it with bxi plus byj plus bzk, and you pick up each of these components. And so dou bz, dou z. This del dot B, the divergence, it's saying that this is equal to 0. And because of this equality, when we're equating the divergence to a specific value, we end up with an equation which relates partial derivatives to something, right? So that's why this is called a partial differential equation. Partial differential, it is composed of partial derivatives, so it's called a partial differential equation, or in short form, these are called PDEs. And many physical phenomena are actually modeled, or their dynamics and their how they behave in space time are modeled using partial differential equations. Maxwell's equations are one of the first examples of partial differential equations. All right, so with these four equations, we can actually predict light. And the way we do that is we're going to simplify these equations even more. So let's focus on a region where there is no charges and there is no current. That is to say, I'm going to focus on a region where rho is 0. We're going to set rho equal to 0. We're going to set J equal to 0, the current density and the charge density to 0. Now, let's look at this equation. I'm going to pick out this equation, equation number 3, which is how the curl of electric field is related to changes, time change in the magnetic field, time variation in the magnetic field, right? And now we're going to do some symbolic tricks. So let's say I take the curl of both sides of this equation, right? So I'm going to write something like this: del cross. I'm going to take the curl of both sides of these equations. Remember that E is an electric field, del cross E is an electric field. So as a second order derivative, which we covered in the previous module, I can take the curl of the curl, right? So del cross E, and then on the right hand side, we'll have del cross minus d dou B dou T. Now del is composed of partial derivatives with respect to space, and T is a partial derivative with respect to time. It's perfectly all right for us to interchange the order of these operations, and then I can actually push this del operator inside the partial derivative. So the way we and sort of one's way of justifying this to yourself is that both the derivatives are actually linear operations. You can pretty much interchange their order. All right. So the way we can write the right hand side is that it's a partial derivative of not just b, but because we've taken the curl of this expression, it's a partial derivative of del cross b. And on the left hand side, we have del cross e. Now, if you've seen the previous module, I left you with a quick exercise, which is I didn't work out this explicitly, and it was a quick exercise for you to show what the curl of a vector is. And I hope that you've been able to come up with the conclusion that this curl is nothing but the divergence of del dot E, right? So del dot E is a scalar. It's the divergence of E, and I can take the gradient of the divergence. So it's actually del dot E, which is one of the second order derivatives we defined last time. And I was saying that this is real. You rarely come across it in applications, but I was not quite right there. Well, it turns out that it doesn't have a special name because you rarely come across it in a standalone manner, but you do see it. Sort of as an ingredient in sort of let's say when you're calculating the curl of a curl. All right. So we have the gradient of del dot E minus, you'll see the Laplacian of E. And on the right hand side, we have minus dou T del cross B. So this is coming from equation number 3, Maxwell's equation number 3, right? We took this equation and we took the curl of both sides. Now we have set J equal to 0, right? Now if I look at equation number 4, maybe I can use a marker with a different color. Now if you look at equation number 4, it relates the curl of B. This term we have already said is 0. It relates the curl of B with the change of electric field with time. So, and you have this constant mu naught epsilon there. So we're going to use this and plug it here on the right hand side here, or rather here. And what we find is that this thing is equal to mu naught epsilon naught, the partial derivative of E with respect to time. Now, if I go back to equation number 1, that equation tells us that the divergence of the electric field is rho divided by epsilon naught. But we are focusing on a region where rho is 0. Therefore, the divergence of E is also 0, right? So this term just drops out. And so what we're left with is minus del square E equals minus. Now we see that on the right-hand side, we have two partial derivatives with respect to time. And you have mu naught epsilon naught, which are both constants. So it's just minus mu naught epsilon. So they just come out of the derivative, and the second derivative of E with respect to time. Now we are minus on both sides, so we can cancel these two terms. And this equation is an example of what is called a wave equation. So this is again a partial differential equation. It relates spatial derivatives of E with the time derivative of E. And this is a second order partial differential equation. It's a linear partial differential equation, and we'll talk about these ideas in future modules. But this particular form of the equation is called a wave equation. And it tells us that electric field actually propagates in the form of a wave, or rather variations in electric field propagate in the form of a wave. Now, this equation, if I were to write it in expanded form, will look like tau to E tau t squared. So I'm going to just write this on the left-hand side equals 1 divided by mu naught epsilon. I'm going to take this on the other side. And then inside of this, I'm going to expand the del operator. So it's tau to E dx square plus that. This is oh, by the way, you recognize that this is just the Laplacian. This is also the this is also one of the second derivatives we worked out in the last module. That's the Laplacian. So it's tau to E tau y square plus tau to E dc square. This is a full form of the wave equation, the electromagnetic wave equation that we have just discovered. Now, there's one thing that we need to be a little careful about, which is that the electric field here is itself a vector, right? So when I'm writing this expression, what we mean is that we can expand out E in each of its different components, say the X component, the Y component, and the Z component. And this equation, component-wise, if you equate, will give us three different equations for each of the three components of E. But for now, we need not worry about that. What we ended up discovering is what is called the three-dimensional wave equation for how the electric field or variations of the electric field propagates in space and time rather. Now from here, you can actually derive what would be the speed of light in vacuum. And all we need to sort of derive that is some dimensional arguments. So if you look at both sides of this equation, you see that the electric field is appearing in the numerator. And whatever its dimensions be, the numerators, if I'm equating two terms, if left hand side is equal to right hand side, the dimensions, the physical dimensions of both sides should be the same, right? So in the numerator, we have electric fields which all have the same dimension. In the denominator here, on the left hand side, I have two derivatives of time. Now, if you remember the definition of, say, the derivative of a function, so if I take the first derivative of a function, say I'm going to write df dx, that's of the form fx plus del x minus f of x divided by del x. So whatever be the dimensions of f, the denominator will have dimensions of space if I have del x. If I have time, say if I'm taking the derivative with respect to time, then we'll have something like ft plus delta t minus f of t divided by delta t. So the denominator will have dimensions of time. If I were to take two derivatives, the denominator will have dimensions of time squared. There'll be time squared, right? So the left-hand side, and the way to see if you want to work that out explicitly, it turns out that two derivatives with respect to time will have an expression of the form ft plus del t plus ft minus del t minus 2 of ft divided by 2 delta t square. So the denominator will have dimensions of time squared. So the left-hand side here has dimensions of time squared. If I look at the right-hand side, I have, again, second-order derivatives, but each of these terms is a derivative with respect to space. So the denominator on the right-hand side will have space or length squared. So just to emphasize that these are dimensions, I'm going to use these square brackets. So this denotes dimensions of time squared. This denotes dimensions of length squared. And then we have some constant here, which has a form 1 by mu naught epsilon naught. That means that if I were to figure out what is the dimension of mu naught, or rather dimension of 1 over mu naught epsilon naught, it turns out that 1 over mu naught epsilon naught, just for dimensional consistency, this is time square, this is length square, should have dimensions of length square divided by time square, so that both sides of the equation are the same. And length divided by time is just speed. And so length square divided by time square will have dimensions of speed square. So it turns out that the speed that we are trying to figure is given by 1 over the square root of mu naught epsilon naught. And if you work out this, if you just Google or search what the permeability and permittivity of free space is, or that of vacuum is, if I get my dimensions right, then mu naught is approximately 1.25 into 10 to the power minus 6 in standard international units, which you can check. Then epsilon naught has magnitude something like 8.85, 10 to the power minus 12. And if you, again, in standard international unit, and if you plug this into this expression, you'll get something like 1 by 1.25 into 8.85 into 10 to the power minus 18. That's approximately, so 10 to the minus 18 goes to the numerator, and we can write this as 10 to the power 9 divided by, and this product is approximately, I think, somewhere around 11, which you can use a calculator to check. And this will give us something of the order of 0.3 into 10 to the power 9 meters per second, which is 3 into 10 to the power of 8 meters per second. And that's approximately the speed of light in vacuum. So, so you see that with just the kind of mathematics we have developed so far, we are able to derive the wave equation for electromagnetic waves. And by the way, you can do exactly the same calculation. Instead of starting with del cross E, you can start with del cross B and derive the wave equation for propagation of changes in magnetic field. So they work exactly the same way. So we're able to derive the equation for an electromagnetic wave. And just by using the fundamental constants, we're able to figure out what the speed of light should be. And I think there's nothing more magical than being able to do that with the mathematical machinery that we have developed so far. So I hope you found this this module interesting. And that brings us pretty much to the conclusion of this course. I hope you had a good time, and please feel free to reach out to us if you have any questions. Please do try out some of the quizzes we have. If you want more practice questions, please do message us. I'll be very happy to share some more practice questions with you. And hope to see you soon again. Thanks for watching.